Section 2 is about looking at conditional probability, and we're going to be using frequency tables to do that. So the objective today is I can find the probability of an event given that another event has already occurred. We're going to start with looking at this data about Monday Club memberships by grade. This is a frequency table. It's a table that lists kind of a combination of information. So I know that from this table that I have 3 sophomores in drama, I have 6 juniors in drama, I have 8 seniors in drama, and I have 17 kids in drama altogether. And so this tells me about drama, science, and art club, and they're saying I'm going to choose somebody randomly. What's the probability that they're a junior? And so since I'm just choosing some student, it would be there are 40 total juniors out of 115 total students. And that is a fraction that I can reduce, so I would get 8 out of 23 if I divide top and bottom by 5. Okay, so it's pretty likely that I'll get a junior, about a 1 in 3 chance that I'd pick a junior. So then the second question is, this is probability of choosing an art club member. So that would be 58 art club members out of 115 total students. This is not conditional probability. This is just reading the table, but I wanted to make sure you could read the table before we started. Now these questions are conditional probability. This is what's the probability that you choose a junior given that you chose an art club member. So I chose an art club member. What's the probability that I got a junior? This time I'm only choosing from this group of students. 16 of them are juniors, but I only have 58 because I know that they were in art club when I made that choice. I can divide these fractions by 2, so I have 8 over 29 is the probability that I've chosen a junior if I've already picked someone who's in art club. And then the second question is, what's the probability that if I've chosen a junior, I have chosen an art club member as well. So I chose a junior, which means I'm looking at just these students. What's the probability that I chose an art club member? So that would be 16 out of 40. And I can reduce that fraction because I can divide both by 8. So I have 2/5. There's a 2/5 chance that a junior who's in a Monday club is in art club. So I want to make sure that you understand that these are different probabilities because for the first question, I was assuming that they were in art club and I was looking at the probability that they were a junior. And for the second one, I was assuming that they were a junior and I was looking at the probability of them being in art club. So it's a different total number of students. It's the same part. It's still 16 students, but it's a different total. So some notation, the notation for conditional probability, which is the probability that an event occurs given that another event has already happened, is the probability of A, and then we do that straight line given that B has already happened. Okay, here's another conditional probability question. So Diego tracks his sleep and coffee consumption, and we're looking for the probability that he gets 8 hours of sleep given that he had 2 cups of coffee. I would recommend that you pause this video so you can try these ones. The only thing new here is the notation. So this is given that he's had 2 cups of coffee, what's the probability of 8 hours? So we're looking only at this group of data points. So the total would be 24. And I'm looking at 2 cups. I'm looking at just the 8 hours as the part. So that would be 1 out of 6. Okay, pause now and try the other ones and then come back after you have tried those. So this is the rest of the work for that problem. Notice how for these two, 8 hours and 2 cups of coffee, the part is the same, but the total is different because this is the total number of times that he had 2 cups of coffee, and this is the total number of times that he had 8 hours of sleep. All right. So definition about independence. If you have A and B that are independent events, then it shouldn't matter whether B happened first. The probability of A given B is going to be equal to the probability of A, and the other way around. So that's if two events are independent. It also happens to be true that if those probabilities are the same, then A and B are independent events. So if you check the probability of A given B and you get that that's the same as the probability of just A happening, and you check the probability of B given A, and that's just the probability of B happening, then that's enough information for you to say that A and B are independent events. So here's an example. You choose a vehicle randomly. B is the event that the vehicle is black, and V is the event that the vehicle is a van. And we're wondering, are B and V independent events? So one thing we can do is we can check probability of B given V. And we're checking to see if that's equal to the probability of just B. So if I check the probability of B given V, that would be, given that you have a van, the probability that it's black would be 3 out of 3, so 100%. But if I just check the probability of black, that would be 3 out of 22. And these two fractions are not equivalent, so they are not independent events. I want to note that we could have done this the other way around. We could have checked the probability that it's a van given that it's black, and that probability would be 3 out of 13. And then we could check the probability that it's a van just in general, which is still, oh, I did this one wrong. Sorry. The probability of black would be 13 out of 22. The probability of just van would be 3 out of 22. Either way, these two fractions are not equal. So since they're not equal, then we know that those are not independent events. And same for this test. These are not equal, so it's not an independent event. All right, that is section 12.2a. Good luck, have fun.